It's really great for me to have a chance to share this all with you because I'm usually talking to a much more technical audience. So please do stop me if you have any questions or if I use any acronyms that aren't well defined. So just a little bit about Pepperwood if you haven't been there. We opened our doors at the Dwight Center for Conservation Science, which is this LEED certified building that features classrooms, meeting spaces, and places for visiting scholars. We opened in June 2010. Since 2005, we've been operating an educational program in partnership with Santa Rosa Junior College, and as well as with our local public schools. So we're a very dynamic place where we have a very large preserve to do research, educate people about the environment, and one of the things we've been interested in is this question of climate adaptation. And this is a research interest that I brought to Pepperwood when I came in '09. And it really struck me in 2007 when these global climate projections were coming out, and there was a lot of press, and Al Gore's movie was out, well, these are global averages that we're hearing. That doesn't help me at all in Sonoma County to understand how climate change may impact me. So how can we get from a global model and a global estimate to understanding our Bay Area impacts? And here we're looking at a map of maximum July temperatures in the Bay Area counties. So this has been a question I've been thinking about for some time. And this is kind of the situation we want to avoid, right? That we don't prepare in any way, and the next thing we know, we're in sort of an emergency situation. So today I'm going to talk about why we are interested in climate adaptation, why it matters. I'm going to show you some fresh off-the-shelf climate scenarios for Sonoma County that, as far as I know, are the first downscaled climate projections for Sonoma County. I have a whole bunch more maps and graphs and things I'm not going to try to share in 15 minutes, but I can point you to those resources if you want to know more about the science. And then I'm just going to touch briefly on the implications for community resilience. And this really comes out of a partnership that I belong to called the North Bay Climate Adaptation Initiative that I'll tell you more about. And that's a consortium of all these different organizations that have conservation science professionals working together to try to generate these kinds of projections for the community, and then working with different community organizations to think about, okay, well, how does this affect you, your community, your sector? How do you want to use this information? So why climate adaptation? And this isn't the most fun thing to talk about, but the point is, even if we were entirely successful in stopping emitting greenhouse gases tomorrow, we're still looking at centuries of change in our system. So the perturbation or the disturbance that we've put in our climate right now is not going to go away right away. It's creating a little wave that's going to go through the system. So we're going to need to deal with the impacts of climate change. However, this should not discourage us from taking action today, because when you look at the models and the differences between a mitigated scenario where we actually achieve our mitigation objectives and an unmitigated scenario, believe me, you want to live in the mitigated scenario world. The unmitigated scenario is not a world I want to be in, and from a natural point of view, it's a world where California has no California poppies, where California has no California redwoods, and where we start to lose the things that make our home our place. So I assume many people are familiar with this concept of ecosystem services, and this is a terminology we're using to help explain to people what open spaces and wildlands like Pepperwood do for our human communities. And one of the things I want you to leave with today is understanding that the more we look into this, the more we understand that open space and natural areas are going to buffer our human communities from the impacts of climate change. They're going to absorb the floodwaters, they're going to adjust in the way that ecosystems adjust and help buffer us from potentially negative impacts. And I wanted to take a moment just to reflect. We know what a special region we're in, and in terms of my career, it's been so exciting to live in a community where there are so many people with similar background to mine, hopefully a different discipline, but many technical and science people who stay in the Bay Area and want to get involved with local nonprofit efforts and local conservation efforts. So when you go to school and you get your PhD, there's people who are going to do that academic track and be in the academy, which is fabulous, but there's another group of us that choose to work in the community and apply our skill sets to the local scale. And honestly, when I took my first job in Sonoma County and I started working watershed by watershed in the county, I had colleagues saying, well, aren't you kind of overqualified for that? And I was like, well, why wouldn't you want the highest qualifications to work on the local problems? because locally is where we're going to develop solutions. So I'm going to introduce the word of downscaling to you. And the best way I can explain what downscaling means is it means shrinking the pixel size of the images that we have about our climate. So you know when you get a really gross pixel size thing, this shows you what a global circulation model output looks like. And each of these dots is a pixel for temperature. And as you can see, there's like 2 or 3 pixels that represent our entire area. And that doesn't give us a sense of the real diversity of the microclimates of the Bay Area. So this is just showing you a procedure where we can use actual empirical data to make these change elements more fine-scaled such that they start to reflect weather patterns in California. This is at 12 kilometers. But if you blew that up and you were looking at a particular watershed, these happen to be in the Sierras, but you'd still get that pixel effect. And the scientists we've been working with have been able to refine these estimates to the point where we get to something that starts to look realistic. We get to something that reflects your experience walking through the landscape, being in more highly exposed hot parts of the landscape, and then getting down into those valleys where you are more protected. And the nice thing about this is we start to see where the landscape is resilient, and that the microclimates that are created by our topography and our weather here create these pockets of resilience. And it makes the story a little bit less gloom and doom when you understand that diversity. So I'm a hydrologist. My focus is on water. You're going to hear a lot about water in this presentation as a result. And what's nice is we can take those climate estimates of temperature and precipitation and use much more detailed information. This is actually a view looking up Sonoma Valley about what we know at a very fine scale about the shape of the valleys, the kinds of soils that we have. And we can run a model that cycles that water through that landscape and understand how much recharge are we going to get into our groundwater aquifers, how much runoff are we going to experience from the landscape, how much water will stay in the soil, which I'm going to talk quite a bit about, and how much water gets evaporated into the atmosphere. And it's a pretty basic principle in physics that as you add more heat to the system, at any particular time, more of that water is going to be evaporated into the atmosphere. And that's part of what we're finding. So here are, and I'm trying to not show very many graphs, but here are, as far as I know, the first localized projections for Sonoma County. I'm going to show you 4 scenarios for climate. Right now I'm working to generate 69 scenarios for climate. And one of the reasons why we use the word scenario is a scenario is a physically reasonable situation that could arise in the climate. It doesn't mean that we're predicting, when I make a graph that goes into the future, that in 2050, on the year 2050, exactly these conditions are going to happen. But these are sort of a long-term trends. Here it's in decades. Sometimes we do it in 30-year intervals to show where the trend is headed. And within that trend is a very variable distribution that represents the real variability we have in the real world. So what I want to say is this is the temperature graph up here. The top 2 lines are the business as usual scenario. It's probably actually a little optimistic now since our emissions are outstripping what used to be business as usual. And the lower lines, the green and the yellow, are the mitigated scenario. So even though we chose 4 models that were quite different, you're seeing that there's the blue line and the red line are pretty close. And those are pointing to possibly plus 8 degrees Fahrenheit by the end of the century added to our average maximum temperature, our average July maximum temperature. So you take the hottest day of the year on average, and you add 8 degrees Fahrenheit. That starts to get really hot. I think we can all agree that gets really hot. Now, we still are looking at about a plus 5 with a mitigated scenario, but those 2 scenarios are really different in terms of their implications. Now, what we found when we looked at the precipitation picture, and I should say the black line is historic, that's real data. The colored lines are the projections. Here's the picture for precipitation. The models don't agree with each other. That's because emissions don't dictate rain. Rainfall is going to be a product of a lot of complex oceanic processes that different models make different assumptions about. And so I think what we're seeing right now is that with respect to water, we have to be prepared for both extremely dry scenarios and extremely wet scenarios. Because the one thing we know for sure is it's likely to get more variable. And so we're going to have more deviation from our historic average, and And we're going to end up in wet years that we've never seen before and dry years that we've never seen before. So that's sort of the implication of that work. Oops, I went backwards. A term that we came up with that we really like using is climatic water deficit. It was defined in a 1998 paper by a vegetation ecologist. And what the climatic water deficit does is it estimates the amount of water that a plant would have used if it had been available. So you can think of it as drought stress. It's the potential minus the actual precipitation. It's the additional water the plant needed to survive that season. And what you can see is that when we map this climatic water deficit, which we measure in units of water, the dark areas, blue areas, are the moisture areas, and the yellow areas, the drier areas. Look at the pattern of oaks in the South Bay. So one of the really exciting things that's come out of our research is this climatic water deficit term seems to be a real control on where things can grow. Makes sense. One of the things about climatic water deficit, when we started calculating this, and each of these lines represents a different major basin of the North Bay. So at the top we have Sonoma and Napa, which are the hottest basins. Then we have Petaluma. Then we have Marin, what we call the Bay or the east side Marin, and there's coastal Marin. So we start to have projections that show you the difference between places that you know these places are different from each other. But the climatic water deficit actually increases more steeply than just temperature. So as much as temperature is going up, it's a nonlinear relationship where the climatic water deficit gets more intense. So the challenge, as usual in California, is you're getting all your rain when you don't need it, and when you really need it, we will most likely have more arid conditions. So this was an important thing to explain to people, because up till then the water managers were like, hey, we may have a whole bunch more water or a whole bunch less, but the point is we're still going to have a whole bunch less at the end of the summer, even if we had more to start with. And that's going to drive a lot more demand for irrigation. And we've been able to map this, that we look at the climatic water deficit of a watershed. It correlates really well to what water users end up needing to use. One thing that really is mysterious is fog. And this has been another really exciting outcome of our research that is now triggering an international effort. My colleague Alicia Torregrosa at the USGS said we have to start to understand fog, because fog is the difference between coho salmon surviving and not surviving during the summer. Fog is the difference between redwoods being able to persist or not persist, and fog is going to be the difference in terms of human uses of energy to stay cool or not stay cool. So we are right now going to put at Pepperwood, we're getting this fancy fog sensor that's going to start measuring the amount of water that's contributed to our ecosystem as a result of fog, and start understanding how important that can be. So one way I encourage you to visualize our climate of the future is Sam Veloz, who's a colleague of mine at PRBO Conservation Science and is a spatial analyst, said, okay, where in California has the climate that is projected for Santa Rosa at the end of the century? And if you do that, the place that it looks like we're headed towards is Santa Barbara County. Now his boss, Ellie Cohen, said, don't make them think they're sitting at the beach at Santa Barbara County. It's more like inland Santa Barbara. So when you think about, what I think about is, well, what does that mean for me? As a natural resource manager, it means that my watershed is going to be getting drier. And right now at Pepperwood, we're starting to study the vegetation and start to see if the vegetation is going to start transitioning to more drought-friendly vegetation. We do think that we're going to lose a lot of our woody species and be looking at more chaparral and grassland species moving in. It also means that the wetlands and streams that are have these little newts. One of the things we're proud at Pepperwood is we have all 3 of the California newt species there. What's going to happen to these guys as they are subjected to bigger variations in water? But I also think that it's going to be more important that the role Pepperwood plays in absorbing stormwaters and helping to recharge aquifers is going to become more and more important. And we'll be taking that role on pretty seriously in the Upper Marquest Basin. For those of you who are in the agricultural sector, and obviously I'm coming a lot from the conservation management perspective, but just showing you a sample again of work that's underway right now with my colleagues. One of the things we think is really important for people to understand is that the climate has already changed. We're not talking about just projecting some change, but there's change that's already happened. So they took a look at average climate from 1971 to 2000, and working with a bunch of wineries, they were able to make a map of where you could grow Pinot or Chardonnay in our area. And everywhere you can grow Pinot and Chardonnay is in color. The blue is very late harvest, meaning it's not that warm and it takes longer. And the red and yellow colors are earlier harvest. And so what they're saying is that in the last decade, compared to the previous 30 years, where you can grow grapes has expanded towards the coast. So a lot of times when people think about climate change, they say, oh, well, you're going to go up the mountain or you're going to go north, right? If you're a pika and you have a certain habitat and it gets warmer, you're going up latitude or up slope. But in Sonoma, we go towards the coast because that's where the fog is. So you're going to see suitability areas for growing moving towards the coast. And then you're going to see some of our inland valleys starting to get really hot for producing those products. So it's a change that we can perceive. So what can we do to use this information that we're generating to create climate resilient communities? And I wanted to say, I feel like my colleagues and I are good at generating this information. What we're trying to take on now is the trick of storytelling to get this information to people who can use it. We're trying to not have it end up in a journal article that will be on the shelf in the library at UC Berkeley that none of you will ever have access to. So I don't claim to be an expert in these industries I'm about to talk about, but these are some of the ideas that have surfaced through North Bay Climate Adaptation Initiative. So in terms of water, the good news is the no regrets policies. A no regrets policy is a policy that you do it today, no matter what happens, you're not going to regret having done it. So I think that people very wisely, I have a friend who's the head of the San Francisco PUEC climate program, and he said, yeah, Lisa, well, your projections are nice, but I don't have enough confidence in those yet to spend $1 billion, right? So, when it comes to designing infrastructure, we're probably going to need a lot more of these models and more validation before we're confident to spend $1 billion, but all of these things I put on this list I think are worth doing now, based on the information we have. Diversifying our supply portfolio. I was involved with the Basin Advisory Panel of Sonoma Valley, and that was one of the things that really came across, is that we actually needed to exploit every kind of water that we could use in the valley to have a sustainable picture for our aquifers. And the Basin Advisory Panel process, which I know has now come to Santa Rosa, is a great example of a climate adaptation effort that's not called climate adaptation, but it is climate adaptation because it's looking at how to increase efficiency, get more water in the ground. One of the things our models definitely show is that the groundwater is going to be much more resilient to climate change, right? It's not exposed to evaporation, and it actually can ride out the highs and lows easier. So we want to use those underground storage tanks that are natural. We want to protect our floodplains that are going to absorb those floods that are coming. And we want to restore our marshes. As you can see, most people think about climate change, they're thinking about sea level rise. I talk about a lot of other things because there's a lot of effort going into sea level rise. But that's one of the best examples right now where all around the bay they're starting to do pilots to show how marsh restoration can protect communities from sea level rise. For agriculture, clearly the water issue intersects with agriculture. I've already been giving these presentations to agricultural communities where people come and say, well, what if we work on increasing our soil moisture holding capacity? Is that adaptive? And I was like, yes. How do we analyze the farmland that we have in the county and make sure that we protect those areas that are going to be good growing areas for the centuries to come? How do we start taking advantage of high technology? People always want to hear good news from me. The good news is that we can get information about our environment way more cheaply than we used to because of high tech. And we can use water much more efficiently because of high tech. And then a CAF group, I talked to them earlier, and they're saying, well, one of the things they're focused on is if you're a produce farmer, you need cool and chilled areas to store your produce and to be able to transport your produce. And how do you share those resources? That's going to become more important. And then finally, the issue of pests. One of the things that we're seeing is that the most climate change that we've experienced right now is not actually on those July hot summer days. It's been an increase in warming on our coolest temperatures. Less freezing, warmer winters, we had it this winter, and warmer evening temperatures. And so if we have less freezes, how is that going to affect the life cycle of the insects and pests that agriculture is dealing with, and that also may affect our health? And then finally, health. It was great at the North Bay Climate Adaptation Initiative Summit. We had the Chief Health Officer of Sonoma County. They're not about doubting climate change. They've already built up their heat emergency centers to be prepared for this. So this is an environmental justice issue, in that it's often the poorest communities that are going to have the greatest exposure, and that's something that our community is already working on. And I would also just say emergency response. I mean, we're going to be looking at more fires and more floods, and we've all got to be ready, from both the agencies that work it that way and then your local neighborhood, to be prepared for those situations. So finally, I know I'm just wrapping up. I'm a real believer in nowcasting. This is my passion as a monitoring geek. This is the weather station we put up at Pepperwood. I'm right now working through the North Bay Climate Adaptation Initiative with a whole bunch of preserve managers to get these kinds of climate stations distributed around the whole county, and working with the water agency to better measure our water supply using these stations. So finally, I'm just putting it out there, northbayclimate.org is the NBCI site. If you're interested in working on these issues, we have a stewardship working group that is working with people on how to get projects in the ground that can help us be more climate adaptive. So there's the take-home messages, and thanks very much for having me.
This is normal. Okay. I'm not. Couldn't hear the microphone?
So Kelly, do you have this set up on people, or do you turn on for it to work? Okay. And I would
That's
definitely
right.
suggest using it.
Actually,
It wasn't a hard
I
to
feel like
work
it's
here.
okay. This-
We have no time, so you have to.
Serious?